हेलो एवरीवन एंड वेलकम यू ऑल फॉर टुडेज क्लास। कल हमने आप लोगों से डिस्कस किया था वेरियस टर्बुलेंस थ्योरी। टर्बुलेंस की थ्योरी जो बहुत सारे रिसर्चर्स ने दी, इसमें तीन रिसर्चर्स मेन है। इसमें बोजिनेस्क थ्योरी of the eddy viscosity concept and frontal mixing length theory and von Karman similarity theory. All these theories, when we combine together, are very efficient in predicting turbulence in different types of flow. Turbulent flow in pipes, turbulent flow in open channel. So these are although based on the modeling and experimental observation, but these theories are very efficient in describing turbulence phenomena in pipes and different types of pipes, open channel and closed channel. So today we are going to discuss what is how we measure intensity of turbulence, degree of turbulence, and scale of turbulence, by which we can measure कितना ज़्यादा turbulence strong है. How we measure? So there are parameters by which we can measure the degree intensity of turbulence. There are intensity of turbulence, degree of turbulence, and scale of turbulence. These are three major parameters by which we can define turbulence. So turbulence is a natural phenomenon. Most of the time it is a natural phenomena when there is a flow in ocean, flow in river during rainy seasons, and normal flow through pipes. Most of the time it becomes turbulent to laminar to turbulent. Even in laminar flow at intense level, flow is not totally laminar, but initially it becomes turbulent. Then, after a certain distance traveling through the pipe, it becomes laminar because when velocity Reynolds number is less, Reynolds number are less. When Reynolds number are less than 2000, less or equal to 2000. 2000 to 2300. Flow is always laminar through pipe. In pipe flow, if when Reynolds number is between 2000 to 2, when it become more than 4000, it become a turbulent flow. But even in laminar flow, when flow enter in the pipe, so initially flow is turbulent and gradually it become laminar because viscous forces. We know that Reynolds number is a ratio of inertia force to viscous force. Viscous force means when Reynolds number is less, viscous forces are more dominant. When viscous forces are more dominant, initially at the entry of the flow through pipe, flow is turbulent, but it gradually becomes laminar because viscous forces dominate over the inertia forces. Viscous forces dominate over the inertia force. That's why flow become gradually laminar. If we want to represent it, how viscous forces become laminar, how turbulent forces turned into laminar, so we represent it by phenomena. So see it, this is a pipe, and this is a center line of the flow. This is the center line of the flow, center line of the pipe. Suppose flow is entering from here, entry region. We show here how fluid is entering. Fluid is entering like this. Fluid is entering like this. And if it is a zone, hydrodynamic length, this area is known as hydrodynamic entrance length. Beyond this, fully developed laminar flow. So what happens when flow enters into the region? Initially, it is fully this region. At very intense, it is fully turbulent. So here you see it average velocity, V average. Because V average remains constant. As we move forward, we reach here. Now flow become like this. And again, laminar, this is a turbulent flow, but here you can see average velocity remains constant. And here it is a V maximum. Flow is gradually turning into turbulent, turbulent to laminar. Initially, it is a fully turbulent. Again, here V average remains constant because same quantity of fluid is flowing, so average velocity remains constant because quantity of discharge is same. As we move forward, again we move here. So from here to here, you can see take distance from here. So gradually flow is becoming laminar, more and more laminar, more and more laminar. And when we reach here, you see that fully flow is, sorry, here you see fully laminar flow. This is fully in beyond this region. And here you see laminar V maximum, U maximum, and average velocity remains constant. So here V average velocity remains same throughout the flow, because whether it is laminar or turbulent. So here you see that V average upon U maximum for fully developed laminar flow is 1 by 2, and we always see that in pipe flow. For laminar flow through pipe, average velocity to maximum velocity is 1 by 2, because this is a zone hydrodynamic entrance length up to which flow is not fully laminar. But as we move, and this length is ending here, and now full flow is becoming fully laminar. This is a laminar flow, although at entry level it is a turbulent. And as turbulent, because viscous forces dominating over the turbulent forces, inertia forces, because initially inertia was very high, and viscous forces dominating over the inertia forces. So after hydrodynamic entrance length, it becomes fully laminar flow. And for laminar flow, it is a maximum velocity here we reach here at the center line. This is the maximum velocity at center, and this is average velocity. Ratio of average velocity to maximum velocity is 1 by 2 for the laminar flow. And for the fully turbulent flow, V average upon U maximum is around 0.8 to 0.85. So this ratio for turbulent flow is always greater than ratio of average velocity to laminar maximum velocity. For turbulent flow is always greater than ratio of average velocity to maximum velocity for the laminar flow. So we can say here U average, or we can say V average. We take V average upon V maximum for turbulent flow is greater than V average upon V maximum for the laminar flow. This is, you always remember, this is very important discussion for difference for laminar flow and turbulent flow. So what is a kind of what types of the laminar turbulent flows are there? Simply we can broadly define laminar flow, turbulent flow in three categories. Turbulent flow in three categories. Number one, wall turbulence. It is very close to the surface of the. This is very close. Suppose in this region, because we know that whether flow is turbulent or laminar, and in very close to the wall. This is a wall, and very close to the wall, it is always a laminar, but we are very close. Suppose this is up to this, here up to this point, this is laminar, but from here very close to the wall, it is a turbulent, because it is effect of the wall. Due to effect of the wall, turbulence is known as a wall turbulence, which is very close to the wall, but not from very high distance from the wall, but very close to the wall turbulence is known as a wall turbulence. And number two is a free turbulence. Free turbulence means away from the boundary layer created due to wall, because surface boundary layer in which effect of surface is there, and beyond surface boundary layer flow become free turbulence. Means it is a kind of turbulence which is you can see some formation of eddy currents, some suppose jet in wake, suppose flow is over the cylinder or the sphere, you see that wake generation, some wake which will generate over this flow of the cylinder and sphere. So it becomes free turbulence. Means you can see some eddy currents, some reverse flow, that kind of where effect of the boundary layer is not beyond the boundary layer, because boundary layer always far near the wall. And beyond this boundary layer, flow become turbulent. Flow become free turbulence. This is known as a free turbulence. Third one is a free turbulence, and third one is known as a free turbulence, convective turbulence, turbulence. Convective turbulence means convectional current between one layer to another layer, from lower layer to upper layer, convection current. Suppose this is a region where convection is taking place. This is region, upper layer, lower layer, fluid coming from here to here, backward flow, forward flow. Convection means from lower layer to upper layer to lower layer. This type of reverse flow will take place. That is known as a convective turbulence. There are three main turbulence you find in flow through pipes. पाइप के में जो फ्लो होता है उसमें तीन तरह के turbulence होते हैं. Wall turbulence, very close to the wall, within boundary layer, and free turbulence means beyond the boundary layer, and convective current due to convection between two layers, upper layer to lower layer to upper layer. That type of turbulence is created. This is mainly eddy formations, reverse flow due to eddy formations. This kind of flow. So these are three categories by which we can define types of turbulence. Now next one is how we define turbulent phenomena by measurement of by using scale. How we can define intensity, मतलब कितना wide level पर कितना भारी turbulence है, what is a magnitude of turbulence. So we have certain parameters by which we can define a level of turbulence. So let us see next page. We see next page. So first thing that we have to define turbulent phenomena, because we know that turbulent phenomena mean velocity we have to find out, because throughout this flow phenomena there is a velocity fluctuating in all directions. Whether if flow is three-dimensional, the velocity will fluctuate in three dimensions, but we will take only that velocity is fluctuating in two dimensions, one dimensions, because in pipe flow velocity is along the length of the pipe. So we see that here main component direction of flow is f direction, and in y direction y component may fluctuate. So we take one directional flow in pipe, and for that we take consideration how different parameters we can derive. So let us see, this is x and y. Here y we denote velocity, u velocity, and here time. On x-axis we show time, and y-axis that is a velocity. We take a line, constant line here. This is a mean velocity line, and there is a fluctuating velocity. You see this is a fluctuating velocity, and this velocity flow in x direction, and you see that component are fluctuating. So this one is a mean velocity u, this one with mean velocity, and this one is a instantaneous velocity. And we suppose there are 2 points A and B, and between these 2 point time interval we take dt. Dt is a time interval. Dt is a time interval between point A, because we see that reversal up, because you can see velocity is fluctuating along the x direction. So this is a u, and this one is a ui, instantaneous velocity. Instantaneous velocity, you can see upper level, this is also instantaneous velocity ui, and this is also instantaneous velocity ui. This is lower value and upper value, but this is always fluctuating, and fluctuating due to fluctuating component ui. This upper value you can see it is equal to u plus u dash, because of the fluctuating component you can see velocity is fluctuating. So all we have taken only one direction, that along the f direction it may be, you can take a three-dimensional case x, y, and z, because velocity may be along direction u and v and omega. There are three components are possible, because when flow is very turbulent, fluctuating component may be along f direction u plus u dash, y direction v plus v dash, and z direction w plus w dash. Three components are possible: ui equal to u plus u dash, vi equal to v plus v dash, and wi equal to w plus w dash. Three possible. And other properties of the, because it is turbulent flow, so other properties will also vary. Suppose density, pressure, temperature. So temperature, density, Ti equal to T plus T dash, and rho I equal to rho plus rho dash, and Pi equal to P plus E dash. Why? What are these things? Temperature will also change in turbulent flow. So mean temperature plus fluctuating temperature at any time. When velocity is fluctuating, so other parameter temperature, pressure and density will also fluctuate. So we can take mean value. How we get a mean value of this flow? Mean value can define the integration of the instantaneous value. To make it small here first, reduce the size. How we find mean values? Because we know that along the f direction u, velocity along f direction is ui, and this is fluctuating between u plus u dash and u minus u dash. Lower value may be u minus u dash and upper value u plus u dash. So what is the mean value? That is u. U equal to how we find 1 upon time interval, total time interval. We can take total time interval is t from here to here. Suppose we are integrating for whole of the time. पर पूरे फ्लो के लिए जो टाइम इंटरवल है टी है, तो पूरे टाइम के लिए इसको इंटीग्रेट करेंगे एंड टाइम से डिवाइड कर देंगे 0 to t एंड यू आई डी टी दैट इज इक्वल टू यू. Similarly, you can find out v equal to 1 by t 0 to t integration vi dt, and you can find w 1 upon t 0 to t wi dt. In this way you can find out mean value, and other parameters of mean value you can also find out. Suppose you want temperature, suppose you want to get P, pressure, 1 upon T, because it is also varying 0 to T Pi dt. So in this way we can get mean values. But how we get mean values? If we integrate average value, u dash, integration of average value. If you integrate u dash average equal to क्या 1 by t 0 to t u dash dt. This is always 0. Because why it becomes 0? For fluctuating, because either it is going plus or minus, plus minus, plus minus. When you add all plus minus, it becomes 0. Similarly, when we add v dash average 1 by t 0 to t v dash dt, it again becomes 0. Similarly, omega dash average equal to 1 by t 0 to t omega dash dt. So average of fluctuating component for whole of the flow is always 0. You can imagine from this one, you see that once it is going u dash plus and again going u dash minus, u dash plus, u dash minus, u dash plus, u dash minus, it will become 0. So average is always 0. But what is not 0? That is a u dash square average. Square of the mean of the square of the fluctuating component will not 0, because minus square and plus square always plus, minus square or plus, so this value is never 0. So if we integrate u dash square, that is equal to 1 by t 0 to t u dash square dt. So this is not 0. That average we have to find out, because degree of turbulence and intensity of turbulence we will define by this square of this value, because fluctuating component, square of fluctuating component velocity, average of fluctuating component velocity and square is never 0. So we have to find out degree of turbulence. Let us see what is a degree of turbulence. Degree of turbulence. How we define degree of turbulence? So degree of turbulence. Turbulence is defined by arithmetic mean of the square of the fluctuating component. Is known as a degree of turbulence. Arithmetic mean of the square of the square of the fluctuating component of turbulence in x, y and z direction is known as degree of turbulence. Means it is equal to under root square root of the mean, square root of the mean of u dash square plus v dash square plus w dash square. Because we have taken arithmetic means, so we divide by 1 by 3. So this is known as a degree of turbulence. Arithmetic square root of the arithmetic means of the fluctuating component along f direction, y direction, z direction is known as a degree of turbulence. u1 square, v1 square is average, omega dash square average. So it become a degree of turbulence. Degree of turbulence. It is known as a degree of turbulence. Means square root of arithmetic means square root of arithmetic means of the square of the mean values of turbulence. U1, V1 square, W dash square. Because already we saw that these values are not zero. Omega dash, this average will zero. U dash average equal to 0 and V dash average equal to 0, but square are not 0. When we add together and take mean and then take square, then take square root, then it become a degree of turbulence. That is a measure of turbulence, degree of turbulence. Another term is intensity of turbulence. Second is intensity of turbulence. Intensity of turbulence. Intensity of turbulence. It is a ratio of degree of turbulence to the flow velocity. Flow velocity, magnitude of the flow velocity means 1 upon V. V is a flow velocity of the whole, because there are x component, y component and z component. So V become under root U square plus V square plus W square. This root is known as a V. So when we divide 1 by V, and that is in under root, it become under root 1 by 3 U1 square plus V1 square plus omega square. Not U, V1, U1. So this become a intensity of turbulence. This is ratio of, this will have, this is dimensionless number. This one is a because unit of this one is also V, meter per second, and unit of this is also meter per second. So this become this is a parameter that is a dimensionless number by which you can define level of turbulence. What is the level of turbulence or magnitude of turbulence? So this is by dimensionless number and it has dimension meter per second. This has dimension meter per second, but this is a dimensionless number. So there are two ways by which we define size of the turbulence. Either we define degree of turbulence or by intensity of turbulence. Another parameter is there by which we can define, that is a scale of turbulence. What is a scale of turbulence? So another parameter is scale of turbulence. Third one is a scale of turbulence. Third one is a scale of turbulence. Scale of turbulence. Turbulence. You see that in turbulent flow, there is a reversal going from mean value. This is the mean value U, and velocity are fluctuating between mean value, upper value and lower value, and between upper value there is a reversal taking place between these two values, going down from mean value and going up at this point. So this is point A to B. A to B are 2 points where direction of velocity is changing or fluctuating. Direction of instantaneous velocity changing at this point, because from mean value going down and from mean value going up. So this interval is equal to dt. So what is distance traveled in this interval? That is known as a scale of turbulence. Distance traveled between two reversal of velocity, two reversal of instantaneous component, instantaneous velocity, about mean velocity. कितना डिस्टेंस ट्रेवल कर रहा है, जब ये रिवर्सल हो रहा है ए से बी के बीच में कितना डिस्टेंस ट्रेवल कर रहा है, दैट इज इक्वल टू यू मीन मल्टीप्लाइड बाय dt. That is a scale of turbulence, udt, because time interval is dt and mean velocity between here and here is u. Again mean velocity u, so udt is known as a scale of turbulence between two reversal about the mean velocity. So this is a concept of defining turbulence, type of turbulence, level of turbulence, how much eddy currents are moving. So if eddy currents are heavy, then fluctuating component will be more, and also this scale of turbulence will also go high. And in turbulent flow you can also define energies. Energy कितनी turbulence में है, total energy कितनी हो जाएगी? Total energy of turbulence for fluid which is turbulent in all directions, you can define it 1 by 2 U dash square plus 1 by 2 V dash square average plus 1 by 2 W dash square average. So average, you can say 1 by 2 take common, u dash square plus v dash square average plus w dash square average. This is known as a total energy per unit mass. So all, because we have not taken mass, so it is a per unit mass of the fluid flow. So these are various concepts which are used for the defining level of turbulence, type of turbulence. There are three main parameters, that is degree of turbulence, intensity of turbulence, and scale of turbulence, and total energy. Because here it is useless to define potential energy and internal energy. Only main energy of the flow in turbulent motion is kinetic energy only, because velocities are very high and potential energy, any concept of internal energy is very small compared to all energy. That's why total energy we are considering here in turbulent flow is only dominated by the kinetic energies of the flow. So that's all for today's discussion to define what is a turbulent flow and how to measure turbulence level. Measurement, what are the scales by which we define turbulence? These are three scales. One is a degree of turbulence, another one is a intensity of turbulence, that is dimensionless number, and third one is a scale of turbulence. And what is total energy? That is a totally kinetic energy of the fluctuating component only. Thank you very much and have a nice day. Please share and like and subscribe to your friends.